Chapter 10 is about regression. First, we're going to talk about the SD line, and we're going to talk about it because our textbook refers to it frequently. However, it's not actually all that useful. So again, we're only talking about it just because the textbook frequently mentions it. So the standard deviation line is going to go through the point of averages, where your point of averages is the average of all the x values and average of all the y values. And the slope is really easy. It would just be the standard deviation of y over the standard deviation of x. If r is positive, or you just put a negative sign in if your slope needs to be negative. And so, again, you go through the point of the averages, and then for your slope, you just go over one standard deviation of x and up one standard deviation of y. It sounds very logical. Okay. It goes through the middle of kind of your football or the cloud you draw around the point. And it's probably the line that you draw if you had to draw the line through the data just by eyeing it. But it's actually not very useful for predicting the y variable. So again, that's the standard, or the SD line. We're not actually going to use it. It's not all that useful. Okay, now let's start building up what we actually are going to use. First, let's talk about the graph of averages. So what you could do is plot the average y value for each x value in the data. So for example, here's the original scatter plots and for the graph of the averages for the height and weight of the men in the Haynes study. So for example, if you look at this graph, notice they draw the little band in for all the men that are 73 inches tall. And we could go through and find the average. So this is the average for all of those men that are 73 inches tall. So this is the average weight for all the men that are 73 inches tall. And I could put a little X there. And so then I could come over to these 73 inches and go up and put my dot for the average of all the men that are that height. And the little numbers on the graph of averages are how many people were in each height group. So that means there were 37 men that were 73 inches tall, and their average height was about 208 pounds. And we're not really going to use the graph of averages too much either. This is just a precursor. I do want you to remember, what is it called when we graph just the averages? When we graph just the averages, we call this the ecological correlation. And remember that your correlation is thrown off because if you look at just these points, you think your correlation is a lot higher than if you looked at the original data. Now the regression line. This one is very useful. One way to think of the regression line is that it's a smooth version of the graph of the averages. So if these are all the averages, all the points, and you try and smooth it out into the line, that would be your regression line. The regression line goes through our point of averages, so the average of x, average of y, and it's close to each point of the graph of averages as possible. So here's our regression line through the averages of the height and weight for the men in the Haynes study. Just so you can see the difference, here is the graph of the regression line versus the SD line for our height and weight study. So notice the SD line is the dashed line. The regression line is the solid line. Notice that they both go through the point of averages, which I guess must be right about here. But the regression line has a different slope. And again, the regression line gives us better predictions. For our next example, we have some fathers and sons height data. So this is our scatter plot for the original data for the fathers and sons heights. Okay, so again, fathers' heights, sons' heights. Now, if I was to look at just the averages, so these points are the averages. And I draw on the SD line and the regression line, notice that the regression line fits those averages much better than the SD line. What else do we know about the regression line? The regression line is used to predict the y variable when we know the x variable. The regression line goes through the point of averages, but the slope, instead of just being the standard deviation of y over the standard deviation of x, our slope is r times the standard deviation of y over the standard deviation of x. R is our correlation. And so what the regression method tells us is then when x goes up by one standard deviation, so if you go up one standard deviation of x, then you have to go up, you don't go up one standard deviation of y, you only go up r times the standard deviation of y. And remember, r is your correlation. So it's a little bit different. It might not make sense to add in that correlation to you, but we've just found over time that it gives us much better predictions when we go up by r times the standard deviation of y instead of just the standard deviation of y. So for example 79, we want to draw in the regression line for our following information. We have our correlation of 0.7. We have our midterm, which has an average of 75 and a standard deviation of 10. And we have our final grade, which has an average of 70 and a standard deviation of 12. Notice that they already put midterm on the x-axis, the final on the y-axis. So the first thing let's do is put in our point of averages. So that's the average of x, which is 75, and the average of y, which is 70. So let's go over to 75 and up to 70. So this is our point of averages. Then for our slope, remember our slope is r times the standard deviation of y over the standard deviation of x. And let's just make ourselves a note that midterm was the x and finals was the y. So my slope is going to be r of 0.7 times the standard deviation of y, standard deviation of final was 12, divided by the standard deviation of x, which was the midterm, so 10. So my slope is 8.4 over 10. I could simplify this, but I'll probably just leave it in fraction form, because if you remember slope is rise over run. So how much do I go up? So I go over 10 and up 8.4. So we're going to go over 10 and up 8.4. That's what the slope means. So if I go over 10 to 85 and then up 8.4, okay, and then let's do just one more. So go over 10 and up 8.4, and then you can draw on your line. I'm very good at drawing in my straight line. And so we've drawn in our line. Let's see what we can do with our regression line. So this is called the regression method. And we're going to use the fact that the regression line rises only r times the standard deviation of y for each increase in one standard deviation of x. So we can use this fact to predict the value of y associated with the given value of x. So here's our steps. To predict or estimate the value of y when you know the value of x. First, find out how many standard deviations your x value is above or below your average of x. Then multiply the answer to step 1 by r, and the answer to step 2 tells you how many standard deviations the new y variable is above or below the average in the y variable. So example 80, Haynes data for the men 18 to 24 with their height and weight. My correlation was 0.47, my average height was 70, my standard deviation of height was 3. The average weight was 162, the standard deviation of weight was 30. Number 1, estimate the weight of one of these men with no additional information about him. So if you have no idea how tall he is or anything else about him, your best guess is just going to be the overall average because you have no idea how tall he is, the height's not coming into play. Let's just go with our overall average for weight. And the overall average for weight is 162 pounds. So if you don't know anything about him, your best guess is 162 pounds. Now though, let's use our regression method to estimate the weight of one of these men who's 73 inches tall. So remember our steps. First, find out how many standard deviations your x value is above or below the average in the x variable. So 73 inches is how many standard deviations above the average? Well, how do we find how many standard deviations? We have a formula for that, right? So let's write it up by step 1. How do you figure out how many standard deviations you are above or below the average? It's your value minus the average divided by the standard deviation. And since we're interested in x's, we could just put little x's on all of those if we truly wanted to. So 73 inches is, well, 73 inches minus an average of 70 divided by a standard deviation of 3. So it's 1. So 73 inches is 1 standard deviation above the average. Above the height average. And I might just think then that my weight would be 1 standard deviation above the weight average, but it's not. The better prediction is actually to times it by r first. So next we're going to say, okay, well, what is r times z? So our correlation was 0.47 times z, which is 1. So this is going to be 0.47. So we need to be, or we predict, or to do the prediction, we need to know that he is 0.47 standard deviations above the weight average. So how do we figure out what he should be then? We'll take the weight average of 162, add your 0.47 standard deviations, and your standard deviation for weight is 30. So 176.1 pounds. That is our best guess for how much this 73-inch tall guy weighs. We guess that he weighs 176.1. So let's try it again. Example 81. So again, we have our same data. R is 0.47. We have our averages and heights for our average and standard deviation for heights and weights. So let's estimate the average weight of the men who are 64 inches tall. So we're going to do the exact same thing. So first we figure out how many standard deviations they are above or below the height average. So 64 inches is, let's see how many standard deviations that would be. So 64 minus the average divided by the standard deviation, that would be -2. So 2 standard deviations below height average. Now we need to times that by our correlation. So R times Z is 0.47 times -2, which is -0.94. So he should be 0.94 standard deviations below, since it's negative, the weight average. Well, how do you find that number? Just take the weight average of 162 and minus our 0.94 times the weight standard deviation of 30 pounds, which is 133.8. Now let's estimate the weight of one of these men who is 69 inches tall. So first let's find our z-value. So 69 minus the average divided by the standard deviation. And all of this is for height, because that's what we're working with right now is height. So this is negative 0.33. So negative 0.33 standard deviations. Or I'm just going to say 0.33 standard deviations below the high average. Now we need to times that by our correlation. So R times Z, it's going to be 0.47 times our negative 0.33, which is negative 0.15. So he should be .15 standard deviations below the weight average. Let's see what that would be then. So the weight average is 162, and then we need to minus our 0.15 standard deviations for the weight. And this gives me 157.5. So we expect him to be about 157.5 pounds. Now he's probably not going to be exactly 157.5 pounds, but this is our best guess. Let's go on to our next example. This comes from the same data set, but now we're looking at the relationship between height and blood pressure. So we have our average height of 70 inches, standard deviation of 3 inches. Our blood pressure has an average of 124, standard deviation of 14, and the correlation is negative 0.2. Let's estimate the average blood pressure of the men who are 6 feet tall. So 6 feet tall is, let's see how many standard deviations we're talking about. So 6 feet is 72 inches minus our average of 70 divided by our standard deviation of 3. So this is 0.66 standard deviations above the height average. But now we need to times it by our correlation. So R times Z. R is negative 0.2 and Z is 0.66. So negative 0.13. So we need to be 0.13 standard deviations below the blood pressure average. Let's see what that would be then. The average for blood pressure is 124 and standard deviation is 14. So if we start at 124, but then we're supposed to be 0.13 standard deviations below it, it would be negative 0.13 times 14. So this gives me 122.8. 18 mm. So what does this mean? This means that we estimate the average blood pressure of 6 feet men to be 122.18 mm. So let's go through just a couple notes on regression. First of all, there are two regression lines technically. So you could regress your y on x or x on y. Basically that just means you can switch your x and y variables. So on this example you have speed versus stopping distance or stopping distance versus speed. And even though your correlation is the same if you switch your x and y variables, the regression lines are not. So you have two different regression lines if you switch your x and y variables. So again, for our example, notice we switched speed and stopping distance for the x and y variables, and the line changed. First of all, your points changed and the line changed as well. So two different lines. Or in example 84, instead of doing two different graphs and actually switching which variable went on the x and y axis, you could regress the other way. So you can do a regression line for predicting the midterm from the final grade, or you can do your regression line for predicting the final from the midterm. So notice you have two different lines. Isn't that interesting? If you are trying to predict the two different variables, your lines change. Also, you have this standard deviation line that we don't really care about much, and that's kind of in the middle. So let's actually see what happens, or how you could do your two different regression lines. So we have the scores for a certain class are summarized. So we have our midterm scores and final scores with our average, standard deviation, correlation. So number one, let's estimate the final exam score for someone who got an 87 on the midterm. So we want to estimate the final. So that means that y is the final, because we want to estimate the final. So x is the midterm, and y is the final. And we're going to do the exact same steps we've been doing. So if they got 87 on the midterm, 87 is, let's see, 87 minus our average for the midterm is 75, over standard deviation for the midterm is 10. So 1.2 standard deviations above the midterm average. Now let's times that by our correlation. So r times z is 0.7, r is 0.7, times our 1.2, which is 0.84. So we need to be 0.84 standard deviations above the final average. So my final average was 70, and I want to be 0.84 standard deviations above it. So 0.84 times the standard deviation for my final is 12. So this is 80.08. So if they got an 87 on the midterm, our best guess, or the average for all the people who got an 87 on the midterm, should be about 80.08. Now let's change that up. Let's do the same process, but now we want to estimate the midterm score for someone who got an 80 on the final. So now we're switching our x and y variables. So now we want to predict the midterm score. So y has to be the midterm. And x is what we're using to predict it, so we're using the final scores to predict the midterm scores. And now we do the exact same steps. So 80 is, let's see how many standard deviations. 80 minus, now we're going to use the information for the final, so 80 minus 70 over a standard deviation of 12. This is 0.83, so we're 0.83 standard deviations above the final average. Now let's times that by r. So 0.7 times our 0.83 equals 0.58 standard deviations above the midterm average. Let's see. So my midterm average is 75 plus our 0.58 standard deviation. So 0.85 or 0.58 times our standard deviation, which is, let's see, standard deviation of the midterm is 10. So this is 80.8 for our midterm score. So that's interesting. When we predicted, used our midterm as our x and y as the final, we had 87 on the midterm and about 80 on the final. But when we switched our x and y variables and predicted, we had 80 for the final and about 81 for the midterm. So it did change. So again, if you use different regression lines, you're going to get different answers. Another thing to keep in mind is that regression lines should only be used if we have a linear association between the variables. So in this example, notice that our data kind of follows a curve. You could try to plot a regression line, but it's not going to do you any good because it's not actually going to follow the points, because the points don't follow a line, they follow a curve. So don't use a regression line if your points follow a curve. The next thing is the regression effect. So if you've ever heard about regression towards the mean, you might have heard it used to describe the fact that extremely tall fathers tend to have sons that are still taller than average, but not quite as tall as their dads. Or on average, when fathers are short, their sons will be slightly taller than their dads. And Sir Francis Galton noticed this in the late 19th century, and he called it regression towards the mediocrity in hereditary stature. A similar example to this is testing and retesting situations. So in test-retest situations, people with low scores tend to improve, and people with high scores tend to do worse. Why? And this is the same why that happens with our heights for our fathers and sons. The why is chance error, because remember, your observed value, what you measure, is your true value plus some kind of chance error. And your chance error can be positive or negative. So for example, imagine taking an IQ test twice. If you got lucky the first time, you might get a higher score than you deserved. So your chance error would be positive. But then the next time you took the test, your score would probably be lower because you're not as likely to get a high chance error again. So you might get a negative chance error or just a smaller positive chance error. And so your test is probably going to be lower. Or if you scored very low, you were probably unlucky to some extent. And so your score would probably be higher the next time. So one thing to keep in mind is a regression fallacy. Regression fallacy can be anything when you attribute the regression effect to something other than chance error. So one example is that you could have a group of people that get their blood pressure measured. And only those people that have high blood pressure have to come back to get it measured again. And so we would expect, just naturally, their second measurements to have a lower average than their first measurements, just due to the regression effect, just because they were probably slightly unlucky the first time. And so the next time they get their blood pressure measured, the average is probably going to go down a little bit. And so you have to be careful and not say, oh, because they got their blood pressure taken and it was low, they probably went home and ate better, because maybe they did, but we are going to expect to see some reduction of blood pressure just due to the regression fallacy. So keep that in mind and don't get really excited right away. You need to actually wait and see if there's a true relationship.